Now we're going to get into polynomial functions. So these will have a degree higher than 2. This vocab sheet has a lot of information about polynomial functions. Basically what it boils down to is there are no negative exponents on the variable x. X is not in the denominator, and there are not two variables being multiplied together. You will have a coefficient times a variable with a positive power. Here we have some information about what the graphs of polynomial functions look like. They are continuous, which means you can draw them without lifting your pencil, and they are smooth, so there's no sharp turns like in the absolute value function. Our essential question today, we're going to be looking at interpreting equations of polynomial functions. The first thing we're going to identify is what the shape of the graph looks like. What you can do is think about the two parent functions x squared, which is a parabola, and x cubed, which looks like a snake. If the power is even, it will look more like a parabola. It might have some bumps and waves in the middle. If the highest power is odd, it will look more like a snake with maybe some bumps in the middle as well. Our first example has a highest power of 2. The leading coefficient is positive, so it would open up. So the shape of this graph would be your basic parabola. Part B, we have a power of 1. This is a linear function. The slope is positive, so the line would rise. Part C, we have a highest power of 3. That is our snake function. Again, the leading coefficient is positive, so it would rise up. And finally, we have a fourth power. Leading coefficient is positive, so it will open up, but it may have a little bit of a wave in the middle. Remember to make that smooth. There's no sharp turns in polynomial functions. I started talking about the leading coefficient as we were going over the shapes of each of those last graphs. So think if the power is even, it will look like a parabola. If the leading coefficient is positive, it opens up. If the leading coefficient is negative, it opens down. So that's the bottom row in our chart. Top row is if the highest power is odd. Think about that snake function. It will rise to the right if the leading coefficient is positive, and it will fall to the right if the leading coefficient is negative. Next, we're looking at identifying end behavior. This is what happens as x gets very small or approaches negative infinity, and as x gets very large or approaches positive infinity. So the way we write that is, as x approaches, we use the arrow to mean approaches, negative infinity. So that means as x gets very small, or as we're looking off to the left in our graph, what is this doing? Looking at the highest power and the leading coefficient, I'm going to make a little sketch off to the right. The leading coefficient is negative and the power is odd, so it's a snake function that is falling. So as x gets very small, the graph is rising. So f of x, the function or the y values, are going to positive infinity. That is half of the end behavior. We know what x is doing as it gets very small. So now we need to take a look at what x is doing as it gets very large. As the graph is going off to the right, the function or the y values are falling or approaching negative infinity. Part B, let's create a little sketch of this. Our leading coefficient is positive and our highest power is even. This will look sort of like a parabola. It might have some bumps or waves in the middle, and it's opening up because that leading coefficient is positive. So as x approaches negative infinity, as x gets very small off to the left, the function is increasing or approaching positive infinity. Off to the right of the graph, as x is getting very large or approaching positive infinity, our function, our y values, are also increasing, so they are also approaching positive infinity. Zeros you should be familiar with. Again, a lot of information on here, but basically what it boils down to is the zeros of the function are another word for x-intercepts. So this is where the graph crosses the x-axis, or where the y value, or the output of the function, is 0. We also have some information about turning points. So as we saw on some of our graphs, we had bumps or waves or turning points in the middle of the graph. The number of turning points a graph can have depends on what the highest power is. So looking down here, it says if a function has a degree n, that's the highest power, then you subtract 1 from that, and that's how many turning points it could have at most. It doesn't guarantee it will have that many turning points, but that is the most number of turning points it could have. For example, if a polynomial function has a degree of 5, that is the highest power, it could have at most 4 turning points. It also gives us some information about how many zeros it can have. If the highest power is 5, it can have at most 5 zeros. Again, neither one of those is a guarantee, but it's putting a maximum on how many could occur. Determining zeros, we will start by factoring. In this case, it looks like I could factor by grouping. I'm going to factor out an x squared. And then I will factor out a negative 9. Then I have those like terms of x plus 5. I'll factor those out, leaving me with an x squared from my first term and a minus 9 from my second term. After you are done factoring, you always ask yourself, can I continue to factor? In this case, we have an x squared minus 9, which is a difference of squares. So I can factor that again into conjugates. The highest power on our original function was 3, which means we can have at most 3 zeros. In this case, we factored it into 3 binomials, so we do have 3 zeros. Setting each of those binomials equal to 0, remember that comes from setting the function itself equal to 0. The y value is 0. We're looking for those x-intercepts where a graph crosses the x-axis. So we have zeros of negative 5, positive 3, and negative 3. Write these as ordered pairs. We will, at some point, be putting all of this on a graph. So if you write it as an ordered pair, it will make it easier for you to get it graphed correctly. We were also asked to identify end behaviors, so we're going to look at the term with the highest power. It is a cubic function, so that's a snake. It has a positive leading coefficient, which means it will rise to the right. Our end behavior would be as x approaches negative infinity. As it's going off to the left, the function is also falling or approaching negative infinity. As x approaches positive infinity, as it goes to the right, as x gets bigger, the function also gets bigger or approaches positive infinity. And you have one you try question.